In Chapter 10, we're going to cover a subset of the procedures that you could use when you're comparing two populations. The only parameters that we're going to be comparing are the means. And we're only going to look at two cases. One case is when you know the value of the population standard deviations, and the other case is when you don't. Now, we're not going to be covering other cases other than these two because we want to have enough time to cover simple linear regression. So we're comparing the means between two populations where we're assuming that we know sigma 1 and sigma 2. We'll use a z for that case, the standard normal distribution. And then we're going to be comparing means where we don't know sigma 1 and sigma 2. And there we're going to use student's t-distribution. In Chapter 9, we covered a hypothesis test about the proportion. In Chapter 8, we looked at an interval estimate about the proportion. But we're not going to be covering the proportion in Chapter 10. We're not going to look at a procedure to where you could look at the difference between two proportions. We're only going to deal with the situation to where we're comparing means. Now, the subscript in this case, the mu sub 1 and the mu sub 2, that indicates which population. When it's 1, it's the first group. When it's 2, it's the second group. Now, which one you decide to be the first group is just up to you. But then you have to be consistent about it. But there's only two cases. Either you know sigma 1, population standard deviation for the first group, and sigma 2, population standard deviation for the second group, or you don't know either one of them. Now, we're going to do one example of an interval estimate. We're trying to estimate the difference between mu 1 and mu 2. In this example, we're going to set up the par as being the first group and the wrap as being the second group. But supposedly the par balls, they've been designed to give you more distance, so we would expect the mean for that group to be larger, and the sample information illustrates that on the next slide. There were 120 balls in the par sample, and the average driving distance, the mean driving distance, was 275 yards. In the wrap group, there were 80 in the sample, and the average for the sample was 258 yards. Now, they're giving us the population information. Ordinarily, you wouldn't have information like this, but we're given that sigma 1, the standard deviation for the par group, for that population is 15, and that sigma 2 is 20, that's for the wrap group. But we're assuming that we know the population standard deviation, so we're going to be able to use a z for a formula that connects the two. Now, we're going to take the sample information that we have, and we're going to generate the 95% confidence interval estimate of the difference between the mean driving distances for the two brands of golf ball. Now, we're setting up group 1 as being par and group number 2 as being wrap. Now, we're assuming that par on average is going to be longer than wrap. So when you take the par and you subtract the wrap, it should be positive. If we set up population 1 and population 2 in the opposite perspective, if we said that population 1 was wrap and population 2 was par, then mu 1 minus mu 2 would be expected to be negative. But the way we're setting this up, based on the information that we have, we expect mu 1 minus mu 2 to be positive. Now, if they were the same, it would be 0. So what we're expecting to see is an interval estimate which we have two positive numbers. If there's really a difference here, we're going to come up with two positive numbers. But we're setting up group 1 as being the par, so n sub 1 is a number in the par group. We're setting up group 2 as being the wrap, so n sub 2 is the sample size for the wrap group. And then x1 bar minus x2 bar is going to be the point estimate to estimate what the difference is in the population means. But we're going to have the same general form for an interval estimate. We're going to have the statistic, the point estimate, in this case x1 bar minus x2 bar, plus or minus the margin of error. Now the margin of error is going to be the z-value multiplied times the standard error of the statistic. In this case, the statistic is x1 bar minus x2 bar. But there's a formula based on sigma 1 and sigma 2 for the standard error of the difference of the sample means. Now I put the question of the problem right up in the top left-hand corner. We want the 95% confidence interval estimate for the difference between the mean driving distances of the true brands of golf ball. So sigma 1 and sigma 2, we know what they are. We have the 15 and the 20. So we're going to use the formula. Take the statistic, x1 bar minus x2 bar, plus or minus the z-value. Now the z has a subscript of alpha over 2. The confidence level and alpha, which is a level of significance, they're complements. So if we want the 95% confidence interval estimate, then that corresponds to a 5% level of significance. Half of that 5% is going to be in the upper tail. Half of that 5% is going to be in the lower tail. But alpha over 2 tells you the probability that's in the tail. Now we figure out the z-value that's going to correspond to 0.025 being in the tail. And then the standard error of the difference of the sample means is the square root of the variance of the difference of the sample means. And the variance for the difference of the sample means is sigma 1 squared over n1 plus sigma 2 squared over n2. All you have to do is take the square root of the variance to get the standard deviation. But then we can take the sample information and just do the arithmetic, just plug in the numbers. Group number 1 is the par group, and for the par, x bar was 275. Group number 2 was the wrap group, so the sample mean for the wrap group was 258. So the x1 bar minus the x2 bar, we get over on the top right hand side, we get 275 minus 258. Plus or minus, we're getting an interval estimate. So we're going to have a lower bound with the minus, we're going to get an upper bound with the plus. But the interval estimate, when you put 0.025 in each tail, you're going to get a z-value of 1.96. You just look that up in the z-table. The value of sigma 1 was 15. That's for the wrap group. Excuse me, that's for the par group. So we get 15 squared over the sample size for the par group, which was 120, plus 20 squared over 80. 20 was the population standard deviation for the wrap group. And we just go through there and do the arithmetic, and the lower bound becomes 11.861. and the upper bound is 22.139. So we are 95% confident that the difference of the population means is somewhere in that range. Now, what I put in the little box where I put probability, the probability that that lower bound is less than, ordinarily you would see this written as mu1 minus mu2. But because par and wrap, because they are fairly small designators of the group, I just put those in there as subscripts. But the population mean for the par population and the population mean for the wrap population, I just used the words par and wrap rather than the 1 and the 2. But there's a probability of 0.95 that the difference of those population means, where we're taking the mean for par and subtracting the mean for wrap, that it's somewhere between 11.861 yards and 22.139 yards. Now another way to say that is that we're 95% confident that the mean driving distance of the par golf balls exceeds the mean driving distance of the wrap golf balls by at least 11 yards. That interval estimate runs from 11.861. Well, if I just round this off to whole yards, 11 is the nearest whole number that I know is going to be kind of on the boundary of this interval. It's got to be at least 11 yards. Now, it wouldn't be at least 12 yards because that would be above, that would be inside that interval. But it's not going to be any more than 23 yards. The upper bound is 22.139. So if I go out to 23, it's certainly not going to be any more than that if that 95% confidence level is between 11.861 and 22.139. But actually we're a little bit more than 95% confident that the par golf ball is going to exceed the mean driving distance of the wrap by at least 11 yards, but no more than 23 yards. Now we're going to look at hypothesis test. We just looked at interval estimation. Now we're looking at hypothesis testing when you know sigma 1 and sigma 2. There's a lower tail test where you're looking for less than. There's an upper tail test where you're looking for greater than. And then there's a two-tail test where you're just trying to show that the difference is not equal to some value. The test statistic, you take the difference of the sample means, you subtract whatever the hypothesized difference is, whatever that is up in the null, and then you divide it by the standard error of the sample means, which is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Now once again, we're going to set up the par as group number 1 and the wrap as group number 2, and we're trying to show at the 0.01 level of significance that the mean driving distance of the par golf balls is greater than the mean driving distance of the wrap golf balls. Now mu1 is the population value for par. We don't know what it is, but we just call it mu sub 1. Mu sub 2 is the population mean for the wrap. Now we're trying to show that the mean driving distance for par is greater than it is for wrap. So when we look at the difference, when we take mu sub 1 minus mu sub 2, we're trying to show that that's positive, that that's greater than 0. The value against which we're comparing is 0. When we actually do the procedure, we're going to assume that mu1 minus mu2 is 0. But in the null hypothesis, we're going to set this up that mu1 minus mu2 is less than or equal to 0. Because what we're trying to do in the alternative hypothesis is to show that the difference, that mu1 minus mu2 is greater than 0. We're trying to show that par, on average, is bigger than the average for wrap. Now the procedure for the hypothesis test is the same. What we're going to have is a little bit different notation because we're looking at the difference of two groups, and we're going to have different test statistics. But the hypotheses, we're trying to show that par, that the mean driving distance for par is greater than it is for wrap. So if par is group number 1, then mu1 minus mu2 should be greater than 0. That's the alternative. The alternative is what you're trying to show. Now the null is going to be the opposite of that. If it's not greater than 0, it's less than or equal to 0. But this is going to be an upper tail test. When we get to the point to where we do that critical value approach, we're going to take the alpha value and we're going to put it on the right hand side. So sometimes this is referred to as a right tail test. But group number 1 is par and group number 2 is wrap. The level of significance for the hypothesis test was 0.01. Now we figured out the null and the alternate. We know we're doing an upper tail test. The level of significance is 0.01. The third thing is to calculate that test statistic. So we plug in 275, that's the sample mean value for par. 258 is the sample mean value for RAP. We're comparing against 0. We're trying to show that mu1 minus mu2 is greater than 0. So 0 is the hypothesized value. Sigma 1 was 15, sigma 2 was 20, N1 was 120, N2 was 80. But just plug in the numbers and go through and do the arithmetic. And when we round that off to 2 decimal places, the computed value of the test statistic is 6.48. Now what we do with that number, it's a little bit different depending upon whether we use the p-value approach or whether we use the critical value approach. We're going to need that number in both approaches, so you've got to go through and calculate it. But what we do next just depends on whether it's the p-value or whether it's the critical value. But we're going to go through both of them. Now our computed value is 6.48. This is a z. So to get the p-value, we're going to go to the z-table. Now when you go to the z-table, 6.48 is not there. It's way outside of the values that are in the z-table. The largest value that you have in the z-table is 4.09. The probability for 4.09 is 0.9999978. Now that would be the probability to the left of 4.09. The p-value in this case is for an upper tail test. So we really want the probability to the right, which would be 1 minus what it is to the left. So if that z-value was 4.09, the probability to the right would be 0.00022. Really small number. Now 6.48 is further to the right than 4.09. So the probability to the right of 6.48, it's going to be even less than the probability to the right of 4.09. So we know that the probability to the right of 6.48, it's smaller than 0.0000022. It's certainly smaller than 0.0001. And that means it has to be smaller than 0.01, which is our level of significance. But it's just incredibly small. So we're going to reject the null. Small p-values, you want to go with the alternative hypothesis. Large ones, you go with the null. But because that p-value is so small, it's so unlikely to get a result like this if the null was true, we're going to reject the null. So at the 0.01 level of significance, this sample evidence indicates that the mean driving distance for the par golf balls is greater than it is for the RAP golf balls. Now if we use the critical value approach, we're going to take our level of significance, our 0.01. This is an upper tail test. We're trying to show that mu1 minus mu2 is greater than 0. And you take that 0.01 and you put it in the upper tail. That means that 0.99 is smaller. And you go to the z-table and you look in the body of the table, the interior of the table, and you're looking for 0.99. That value is not going to be in there. But the closest z-value to values that are in there corresponds to 2.33. It's just a little bit closer to that probability value for 2.33 than it is for 2.32. So we're going to use 2.33 as our critical value. Now the rule for an upper tail test, you're going to reject if that computed value, if it gets out in that tail. So this is an upper tail test. So we're going to have to be larger than that critical value, or equal if we're going to reject the null. So you reject if your computed value is greater than or equal to 2.33. 6.48 is quite a bit larger than 2.33. So we're going to reject the null. So the sample evidence tells us that the mean driving distance for the par golf balls is greater than it is for the route. Now, one of the data analysis tools in Excel is a z-test to sample for means. When you open up the toolbox, you go to the data tab, and then usually it's on the right hand side. There's an analysis group up at the top, and one of them in there is data analysis, and you just click on data analysis. The tools are alphabetically arranged, so the z-test is down at the bottom, but just double click on it, or just click on it and select it. Just click on OK, and you pull up the z-test to sample for means tool, and there's a dialog box, and you just put the information into the dialog box, and it will do the procedure for you. This is the dialog box for the to sample for means procedure that uses the z-test. The first box is to put the data in there for the first group. So just select the data A1 through A121. A1 contains a label for par, and then the rest of it's the data values. The information for wrap, that was in B1 through B81. That was group 2. The B1 value was the label, and then the rest of it, those were the data values. We were trying to show that mu1 minus mu2, that's the alternative hypothesis, that was greater than 0. So the hypothesized value is 0. So that's what's entered there. The next two boxes, we need the variances for the two groups. Now the problem gave us the standard deviations. So we just have to take those numbers and square them. For par, it was 15, so 15 squared is 225. The standard deviation that was given for wrap was 20, so 20 squared is 400. Check the box for labels, because we do have the labels in A1 and B1. Alpha for this problem, the level of significance, was 0.01. And then the last thing down there at the bottom, just click on output range, because we want the output to be on this same sheet that has the data. We want that to start in cell D2. Now the output is shown on the next slide. Now we've made column A and column B a little bit smaller than probably what we should, but if you look over in E4 and in F4, the par, comma, inc, period, wrap, comma, limited, period, those were the characters that were in A1 and B1 when the procedure, when it was accomplished. But it starts in D2 and it puts out z-test to sample for means. Now the mean values for the sample were 275 and 258. The variances, that was something that you had to put into the procedure, 225 to 400. The observations, well, Excel just counts those from the data that you select. So there are 120 values for par, there were 80 values for wrap. The hypothesized mean difference was 0. So Excel calculates that z-value for you. Now we rounded it off to 6.48, but Excel gives you a lot more decimal places than that. the p-value for a one-tailed test, you see that 4.4795? You say, well, what's that? P-value? But if you look at the end of it, there's an e minus 11 times 10 to the minus 11th power. Where that decimal point is, 4.4. You take that decimal point and you're going to have to move it to the left 11 decimal places. You have 10 zeros before you get to that 4. I'm not even going to try to say that. This p-value is an itsy bitsy p-value. It's just super small. It's a lot smaller than 0.01. And that's going to tell you to reject the null. In this presentation, we looked at how to compare means between two populations. We looked at interval estimation. We also looked at hypothesis testing. Furthermore, you were introduced to a procedure in Excel, one of the tools, that basically goes through there and does all the calculations for you. You have to enter the variances, but Excel will do the calculations for you. Now in the next presentation, we're going to be doing something fairly similar. We're going to be comparing two populations with respect to the mean. We're only going to look at the hypothesis test part of it in that presentation. But you don't know sigma 1 and you don't know sigma 2. So what you do in that case is you use students' t-distribution. The issue is going to be trying to figure out what the degrees of freedom value is, which turns out to be quite an interesting problem. But we'll get to that in the next presentation.